Once we have used these methodologies to join data that has been collected from different origins, in this case, we've joined a hand-collected data and other machine-collected data. What we're going to do is to compare the different methods and see how this impacts the data. And the other objectives that we have is to show you criteria so that you can define how you can join the data. So the first thing that I'd like to show you would be the distribution by using histograms with the different methods. What you can see here is the first one is the model that has been used in Buffer, the top left square, and the low left is the method that has the observation. So the one on the top is a method that adds the observations, and the second one collects the observations that are here. And generally, these are methods that use the join function. The other two methods that are on the right side are interpolations. So they're like a buffer, but they have different weights depending on the distance. So one is called inverse distance. Simply, it's a weight based on the function of the distance. And it generally has a very compact behavior. And it has some observations also. On the other hand, on the lower right box, you'll see the fact that with a statistical method that uses the information in the variogram in order to apply it to the closest observations when you're obtaining a mean. So once this is done, you can see the distribution is quite different, especially in the case that where there's only one observation. With the closest neighbor, there's a lot of noise compared to the others. This is another representation. This is a correlation matrix where you can see how the different observations have been correlated, taken by different on different distances. Normally, the highest correlations, as you can see there, in the values that have been interpolated, there's less variation in the one that has inverse distance. It's going to be more compact and it's going to be harder to find differences. The method that used by geostatistics is properly aligned with the method that has data aggregation, but at the same time, it does not respond very good compared to the inverse distance. So I would preferably use the system with the buffer or the system with geostatistics. Sometimes in order to run geostatistics, you have to respect certain conditions. And without those conditions, then you have to use the other method. On the other hand, I would not recommend using an observation, the observation that's the closest. Usually when you use machines, there's a little noise in the data. You can see how this data looks, especially when they're high. So I would recommend not using that method. There's another important thing that I have to tell you, and it's how to group the data, what criteria to use to group data. And going back to the sampling, to the hand sampling, that's represented with the blue dots here. Regarding the points that can be joined with a machine with high density, you can take two decisions. You can either interpolate the values that have been hand joined in each one of the points where the observations have been taken with a machine. The other option is that the values of the machine can be used, they can be interpolated to the places where we've taken soil samples. So you can see that that's a strategy and the approach that we've taken in this set. And why have we done this? Because I've seen many examples where the first option takes place, and I generally recommend the second one, the one that you're seeing here in this example. And there's several reasons to do this. The first one is that there's uncertainty introduced by the measurements that are machine made, that they introduced many errors. So what can be observed by hand, it usually has more quality, it takes a higher effort, obviously, but it's got better quality. And these samples are more costly, but also more valuable. They have a lot more weight. On the other hand, there's an uncertainty that depends on the interpolation. If you use an interpolation or data aggregation, this is going to be based on the function of the distance and the number of observations. So if I'm in this red point, I would like to know information about the soil. Probably most of the information is going to come from these two neighbors that are very close. And the uncertainty increases as you are at a longer distance. So there's going to be a higher rate of error here. On the other hand, if you want to take the value of one point where you took the soil sample, we're going to have many observations and they're going to be a lot closer and there's going to be less uncertainty. Another factor to take into account is that the final size is going to change a lot. So in this example, it wouldn't be so important, but there are situations that this could become a problem. So what we're going to do is, once the points have been referenced, they're going to be less points with the support that's coming from the observations that have been hand taken. So as a summary of this session, before aligning the spatial data, it's important to align the projections of the origin data. The alignment method has consequences on the further analysis, and it's important to align data with the spatial support represented in the lower quantity, which are the most valuable. So these are our recommendations to use or collect data. And thank you very much to Nahuel and Agustin for producing this data.